Well, this room is like pretty big size though.
Yeah, but it seemed bigger.
We're all using like a third of it. Okay, so last couple of days we've been talking about logarithms, and I was saying to a couple of you guys earlier, please be patient with logarithms. I don't expect you guys to nail this in like 2 days. Okay, like my best -1 students, it takes a little while to wrap your head around these things. So I mean, we still have like 2 weeks. I think 2 weeks from yesterday is supposed to be when we were supposed to write our unit test. So like we still have quite a bit of time to figure this stuff out. So don't stress if it's not instantly clicking. It is one of those things though where you probably need to do some practice. So I'll find you lots of practice. I'll walk you through it if you want. Today's goal is now to take logarithms and to solve them. If you kind of pick up on the pattern of this unit, it's very similar. I introduce a type of function. Linear, quadratic, exponential, logarithmic. We'll do the same thing next week with sinusoidal. So like I introduce the function, talk about some properties. Then we look at what the graph looks like, right? And then after we look at what the graph looks like, we have to be able to solve for x. Before let's do logarithms, let's do a quick review of how to solve other type ones. Let's say I gave you this equation here. 3x minus 4 equals 7. Could you solve that?
Yes.
Add 4. 3x equals 11. Divide by 3, divide by 3. Cool. Everyone cool with that? All right. Let's say it was quadratic. X squared plus 6x plus 8 equals 0. You have a couple options. One option is a factor.
Which you can do.
Yeah, this one actually I picked on purpose because 4 and 2 adds to give 6. And 4 and 2 times is to give 8. And then hopefully by now you're pretty comfortable with knowing this means x is -4 and x is -2. There's another possibility. I won't take the time to go through it all, but you could use the quadratic formula, which I've said this a few times so far this year. It's on your formula sheet. I imagine that's for a reason. I don't think that they would not test you on it if it's not on your formula sheet. I mean, I can't guarantee that. I don't control the test, but boy, that just seems to be a giveaway to me. So far, so good? Okay. Then we talked about exponential functions, which might look like this. 2 to the power of x equals 4 to the power of -3.
You find like common base.
Yeah. So you say, well, can't a 4 be written as 2 squared?
James Hard and Daniel Young, please come to the office.
You know how you take 4? 4 is equal to 2 squared. Well, now x, well, 2 to the x is equal to 2. What happens to the 2 and the -3? Add or times them?
3 times.
Yeah, so you have -6. And cancel out the 2, cancel out the 2. Ta-da! X is -6. Does that make sense, by the way?
Mm-hmm.
Okay, well, today we're going to do something similar. We're going to talk about different methods of solving things that involve logarithms. Okay. So let's start with my review slide here. A logarithm is a new type of function, but it's very similar to exponents. There's a lot of similarities between the two. You know what? Actually, before I even get to the slide, let me do one more thing of recapping. I want to make sure everyone's on the same page here. If I asked you for the log of 100, hopefully you'd be able to tell me the answer is 2. And the reason why is that there's 2 zeros. That's kind of what I originally showed you. If I told you, find me the log of this number, I don't even know what the number is called, but you should be able to tell me what the log is.
7.
Yeah, 7. Essentially, this question is asking you how many zeros are there. Now, that's how I originally showed you the question. That's actually kind of not fully true. It's better to approach it like this. This is asking you for how many tens go into the number 100. And so, like, you could write it like this. How many tens do you need? I'm just going to multiply a whole bunch of them here until you finally get to the number 100. And you'd say, well, do I need all of the tens written out here? Well, no, that's way too many, right? You need 2 of them. Because essentially 10 squared is 100. So that's why this answer is 2. Does that make sense? We don't always have to do this for things with 10. If I asked you log base 2 of 8, what this question is really asking you is how many 2's are there in the number 8? So you'd say, well, 2 times by 2 times by 2. Let's just do this a lot. How many of them does it take to make an 8? 3 of them, right? Because essentially 2 to the 3 is 8. So therefore that's 3. Does that make sense? Right. So I guess the point I wanted to start with here is the recognition that logs and exponents, they're kind of similar to each other. It's so similar that we can actually see it in their graphs. The graph of a good old-fashioned exponential graph usually looks like this, just kind of grows uphill, takes off like a rocket ship. Logarithmic graphs actually start with incredible growth and then kind of slowly peter off over time, kind of like how my daughter is getting taller now, but like really her most rapid growth spurt was when she was like, you know, a baby, right? Now that she's 3, she is getting taller and taller, but it's slowing down, right? You guys being 17, 18, you're probably not growing all that much, right? So, the point behind this though is if you tilt your head sideways, you can almost see how like these graphs are similar to each other, right? So, back to my slide then. Long story to get here. Logarithm, new type of function, similar to exponents. We're cool with that?
Yeah.
Okay, so new stuff here. There's some rules that I've shown you before. Hopefully you're kind of familiar with them. If you add things, it's like timesing. This is called the change of base rule. If you want to type in your calculator log base 2 of 3, hey guys. Found you over here. It looks like this. You guys remember that from yesterday?
Yeah.
There's another rule that says if you have an exponent, you can maybe pull the exponent down in front, or like you can pull the exponent up top again. But there's one rule that I didn't talk about. It's written right here, and sometimes I skip this one or forget to mention it because it's not on your formula sheet. This is a rule that shows you how to convert a log into an exponent. And I actually have been doing this rule with you. I've just never actually put it on paper in the same sort of way. So I wanted to show you how this particular rule here works. Maybe in a little bit more detail. This has been on different slides, by the way. I think I've had this on a few different slides. Like if I go back here, where is it? I've had this picture right here before. You remember this one? Okay, well, let me talk about this one now for a bit. Let's say that I asked you to solve this logarithm. Log base 3 of 81. Anybody know what the answer is? How many 3s does it take to make up an 81? 4. It takes 4, yeah. I mean, you can just do that by taking your calculator and go 3 times 3, it's not going to do 1. Times 3, it's not going to do 1. Times 3, hey look, it's 81. Okay. Well, essentially, that's what I've just written right here. 3 times 3 times 3 times 3 is 81. Well, how many 3s did I write? I wrote 3 4 times, it's equal to 81. These two expressions right here are considered equivalent to each other. One of them has a logarithm in the expression, and the other one doesn't. And this is kind of a nifty rule that you may need to use in order to solve a logarithm at some point. So do you see how like here it's go log base c? See how this lower number right here in purple is my 3? Well, in the other equation I wrote down here, see how that 3 right here is that guy there? Like it matches up. Hello. Here the x is the blue number. For us, that's the 81 right here. Well, look in the other example. Here's where the x goes. See how the 81 is right there? And then lastly, here's the y. This y right here for us is going to be the number 4. And you see in this example here, the 4 up there is this 4 right here. This is not on your formula sheet, unfortunately. It's a rule that they expect you to be able to like work with in your head. So I had a student once who came up with a really clever idea. They called it the 7 rule. They said if you draw a 7 here, 3 from down here up to the power of 4, and then come back across equals 81. This 3 goes there, and then go to the power of 4 is up there, and then the last thing it touches is the 81. There's a rule for like converting them between each other. That makes sense.
Mm-hmm.
Let me try another example here. Just log base 2 of 32. You want to know how many 2's go into a 32? Yeah? 5.
Did you say how many 2s?
Yeah, because 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. So
then it'd be 2 to the power of 5
yeah.
equals 6.
So that's what we need to do now. I need for you guys to be able to convert this and say that 2 to the power of 5 equals 32. Okay. Well, it's easy with numbers. I want you to be able to do it with letters. If I gave you log base x of y equals z, what this means is x,
To the power of y equals 6.
no, x to the power of z equals y. X to the power of z equals y. Okay. This is the final rule. I've actually kind of shown it to you already. I didn't explicitly state it in this sort of method, but this is what we've always been doing. It's one more rule that you might need in order to solve, which is finally, I'm now finally to the point I want to start with. We need to be able to solve some of these things. So, okay, let's get started. Right, so here's the slide, I guess, what I was just talking about. Being able to convert between a log and an exponent is kind of a nifty trick. Okay, another slide here, I guess, just recapping what I've already recapped. Here you've got y equals log base bx. You see how here's your little base of b? I'm going to write it a little bit differently. Log base b of x equals y. If I do that 7 rule, b to the power of y then is equal to x. That's what these graphs essentially are. Here are the two graphs that are, like they're similar. Like they're almost, they're not parallel to each other, but they're flipped over this line. Okay, so here's my goal then. We need to be able to solve some of these sorts of things. So I'm just going to start with just some basic practice of converting. How can I convert this back into a log? So we also have to go backwards. We need a log with a little number down here, another number here, and a final number here. So use your 7. This number down here to that number equals this.
So then, and it'd be log to the x and 4?
Well, this one's a 4. Because
Oh,
what
that
you're doing
one's
is you're
4.
starting with the 4.
Yeah.
4 goes to the power of x,
So
so this is a
that's
4. That one's the x.
I was totally wrong.
And it equals n. So the way you'd phrase it is log with a base of 4 of n would equal x. Watch the 7 here, ready? 4 is going to go to the power of x, and it's going to equal n. We'll do more, okay? Like I said, please don't freak out if this isn't clicking within like a minute or two. My Dash 1 students struggle with this. So. Okay, here's a statement that actually has numbers everywhere. So we need to write it like this. Log with a lower base of this number equals this number here. Work with your 7. Well, okay, so let's start with the base. What's the base down here need to be for the 7 to work? You're right, it's 3. Because this 3 right here is going to have to go to the power of 5.
So then,
and this number here is 243. So if I can clean it up a bit, it would be log base 3 of 243 equals 5. Yeah. Oh, you don't have them? I guess either take them by hand or go print them in my classroom, I guess. One of the two. Yeah, might be just easiest to take it by hand at this point, I guess. What does this notation then mean? This question says, how many 3's are in 243? 5, right? 3 times 3 times 3 times 3 times 3 should be 243. Does that make sense? Okay, so let's do this one here. We need to write this as a log with a base down in the corner. Then this number goes here, and it has to equal something. What's this base going to be? 2, yeah.
Present producer.
Thanks. Oh. Okay, well then 2 has to go to a power over here.
so -4.
That one's -4. And this is 1 over 16. How many 2's does it take to make a 1 over 16?
-4.
Yeah, here's the reason why. Log base 2 of 16. How many 2's are in a 16? 4 of them. There are 4 2's in a 16. But if it's 1 over 16, you know how fractions are like to the power of -1? Well, that's why it's -4. Does that make sense? You need practice on this, right? This is not one of those things you just watch and go, yeah, I got it. So we'll do more. Let's try to now solve these. So that we can try to solve these exponents here. See how these are written in exponential notation? Let's write them as a logarithm. So we want to write it as log with a base down the corner of a number and tell us what it's equal to.
So
What's this little base down here in the corner going to be?
10.
10, yeah. By the way, if I can point something out, this is called a base of a logarithm. This number right here is called a base of an exponent. So like the bases are actually in the same location. So this right here is a 10. Well then 10 is supposed to go to the power of y, so this y goes right here. And then when you come back with the 7, this is where the 81 is. So the question is, how many 10s are there in an 81? Okay, right off the bat, it's not an even number, right? Because if it was how many 10s are in a 10, there's one 10 in a 10. If it was how many 10s are in a 100, that would be 2. So I'm guessing this is probably 1.7, maybe 1.8. How can I actually calculate it on my calculator?
Log. Yeah, log.
You have two options. If you're running an old school calculator, you could do log 81 divided by log 10. If you're running like Shodi or Thomas, you guys have the TA84 kind of thing, you can do log, actually plug in the base and put an 81 there. What was it? I just guessed. Okay, so that was a little off. Do you see how this is solving now? That's the point of today is if I give you an expression or like an equation, you have to be able to solve this sort of thing. Can you solve this using common bases? You know how like I gave you 2 to the x equals 2 to the 2x, and you kind of like cancel those 2's? You can't really do that here because 81 and 10 don't have anything in common. But you can do some work with logarithms if you're clever. Let's try another example. I need to rearrange this guy. The base of the log and the base of the exponent are the same. That's this little e down here.
And then it equal x.
It's going to equal x, and it's going to be the of 25. Well, if you can, you just then type in log of e divided by log of 25. That'll get you your answer. I should point out though, do you guys remember what log e is? It's actually something very special. It's that natural.
7 something, 718.
Yeah, so log of e, by the way, was known as ln. This is actually the ln of 25. So you can actually use the other button and do ln 25. Both should give you the same thing.
I got 0.31.
I must have done that wrong.
So
Maybe
31
I
seems off to me, actually. Because really, this says how many 2.7s are there, and it's 25.
I got 3.2.
Yeah, I figured it'd be bigger, right? Because remember, e, you guys said that e was 2.7? So this question says how many 2.7s are the number 25? And I would think there's got to be 2 or 3 or something like that.
I wrote it in wrong.
Okay. So you could do it like this. You could do log of 25 divided by log of e. Like that would work.
I did the wrong order.
Is that what you got?
First. I got that.
Or, by the way, you could just do ln of 25. Because log e is ln. So they both do the same thing. That makes sense. Okay. Now, this is also something you might be asked to do. Maybe you have an equation that has logs in it already, and you have to try to solve for x. So sometimes when I show students these questions, they get really freaked out, and they go, oh my goodness, I don't really know what to do. But I just want to point out that this right here, I tell my Dash 1 students this all the time, is just a number. Like log base 264, that's just some sort of value. You can just use your calculator and find it by going log of 64 divided by the log of 2.
6.
That's 6. Why is it 6? Well, this is essentially asking you how many 2's are there in a 64. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. There are 6 2's in a 64. So one like this is actually really easy. You just type her in, right? So how many 4's are there in a 1 over 16? Yeah. I mean, let's talk about why that might work. if you made it log of 4 of regular 16, how many 4s are in a 16? 2 of them. But if it's 1 over 16, then that's like a fraction, right? So it's a negative 2s of them. Or this one, how many 7s are in a 49? 2. So if you get asked a question like this, those ones are actually kind of the easy ones because you don't actually have a lot to do. But here it gets a bit more challenging. Can you type this directly in your calculator? Not really. But what you can do is you can convert the log into an exponent using that 7 rule. Remember that rule where you do like this, which we've been working on for the last little while? This is equivalent to 5 to the power of minus 3 equals x. Make sense? Take this base of 5, make it go to the power of minus 3, that's equivalent to x. Well, can't you just type 5 to the minus 3 in your calculator?
Yeah, it's 0.009.
No. Problem solved.
You want it in a fraction
Or you could make it 1 over 125? No.
Yeah.
125? Okay. Yeah, both would be equivalent. Like it could be this, it could be this. I don't know how to ask it.
What about the next one?
Okay, so let's do the same thing. This x has to go to the power of 2 and equal 36.
So you square root 36.
There you go. Then you square root both sides. It's 6. Now look at that as your answer again. If x is 6, it basically says log base 6 of 36. Well, then you'd ask yourself, how many 6s are there in a 36? You'd say there are 2. Because 6 times 6 is 36. Goodbye. Okay, so the next one. Do the same sort of rule. Take that 64.
16.
Go to the power of 2 over 3. It's equal to x. Well, you have a calculator. Just type that in your calculator. 64 to the power of 2/3 is 16. Or let's just check this another way. Log base 64 16. How many times can a 64 go into a 16? Well, like it can't, right? Because the 64 is bigger than the 16. That's why this is a decimal number. Like it does work, but what you have to do is you have to do 64 to like the 2/3. You get like a part of a 64. That'll give you a 16. You can't have the full thing. How am I doing so far? Does this make sense? Sometimes in math we'll talk about by 3 levels. Have I done this before? There's level 1 where like you get it, or like level 1 is where it goes over your head. Level 2 is where you watch and you go, yeah, I get it. 3 I think is the hardest one where you go, okay, now can I do it myself? Like if I were to ask you, are you like level 1 where it's over your head, 2 where you get it, but like 3 do it yourself, where would you put yourself?
I'm like 2.53. Yeah, I'm at 2.
Okay. Okay, if this still like is like it didn't even make sense that I explained it, can we chat later? Okay. Getting to that 3rd level on this is hard, by the way. Like this is outcome for outcome, this is exactly the same as Dash 1, just so you guys are aware. So it sucks. But I'll work with you guys as much as you need on it, okay? Okay, let's try some more. Could we solve these?
Yeah.
How? What would you need to do?
Log 16 divided by log 2.
Yeah, that's it, right? I mean, you don't have to do much special. Log 16 divided by log 2. Or another way of looking at it, how many 2's are in 16? 4. The more you do, the better you're able to kind of train your brain at this. This is log 64 divided by log 4. Or another way of approaching it, how many 4's are in a 64? 3. So here's some questions that I pulled out of, I don't know, somewhere. Let's try to evaluate each of these expressions without technology here. Log base 3, 1 over 27. How do I do with that 1 over fraction bit? You guys remember?
It's a negative.
Yeah, let's just make it 27 to the minus 1. Ignore that minus for a little while. How many 3's are there in a 27? 3. But if it needs to be 1 over 27, it'll be minus 3. There you go. This guy right here, we're asking how many 1/4 are in a 64. Any thoughts?
No.
I have an idea. Could we write this as log 64 over log 1/4? I write it like that.
Yes.
1/4. We've talked about this a bit ago, right? This is the same thing as a -1, right? What can I do with my -1 though? You can kind of move it like
The other side.
in front. So this is like -1 of log 64 over log 4. Well, hang on. Isn't log 64 over log 4 just log base 4 64? How many 4s go into 64 again?
3.
I think it was 3, right? Right? 4 times 4 is 16, times by another 4 is... So this little bit right here is 3. So I guess it's -3. Like in the same way, you know how this fraction right here made that guy a negative number? This fraction right here just does the same thing. It just makes your answer a negative number, that's all. Someone try it in a calculator. Type that in. Type in log 64 divided by log 1/4. So you'll get -3.
-3.
Okay, let's try this one here. This one's here on purpose. Very purposeful. How many 2's does it take to make a -4?
You get 2.
Well, no, because if it was -2, it would be 1/4. Does that make sense? The negative makes it a fraction. Let's just do some math here. 2 times 2 is 4, times 2 is 8, times 2 is 16. How the heck am I getting a negative number? Does that make sense?
You're timing your
Is
back
that
fraction.
possible, to times a number by itself and have it become a negative number? 1 times 1 is 1, times 1 is 1, times 1 is 1. 3 times 3 is 9, times 3 is 27. Am I ever saying a negative number? Is it possible for this number to be negative? This is impossible. Which actually relates to our graph here. Remember how a log graph works? A log graph starts right here and builds upwards. Are there any x values that are negative? -4 would be if you dropped a line straight down here. Is -4 even possible? You can't do this. You can't take a number and multiply it by a number over and over and over again and somehow get a negative out of it. It's just not possible. That makes sense? What else do I got on here? Most of these are just to kind of show some of the little examples of twists and turns you might encounter. How would you put that together? You guys remember the rules from yesterday? Yeah, you times them together, right? So you'd have log base 2, and then 16 times 2? 32, yeah. And then maybe you can even do this in your head. How many 2's is in a 32? 2 times 2 times 2 times 2 times 2 is 32. Or 2 to the 5 is 32. You need 5. Okay. The other one's a bit trickier though, right?
Well, you don't.
Well, before I divide it, I have another idea. What have we learned about fractions? What do they have for an exponent?
You.
So you could do log base 2 of 1 minus log base 2 of 8 to the minus 1. I can give it a -1 exponent. Hang on, isn't there a rule about exponents? What can you do with exponents? Move it in front. Now you move it in front of this logarithm here.
But that make it a plus.
Yeah, that's exactly why I picked this example here, right? Because a negative with another negative would be a plus, wouldn't it? So what you'd have is log base 2 of 1, double negative log base 2 of 8, which, I mean, skipping a step just means add. Add means times, right? So 1 times 8 is 8. So then my last question, how many 2's are there in an 8? 2 times 2 times 2 is 4, times 2 is 8. So there you go. That is our answer. Okay, now I said this yesterday a lot. It is very possible for you to type that in your graphic calculator. It is very possible for you to type that in your graphic calculator. It might require a lot of brackets and doing it in pieces, but I really want to stress, if you want to get good at this, you really shouldn't just default to like I'll just do the first one just to prove a point. You could go log of 16 divided by log of 2 plus the log of 2 divided by the log of 2. Like, you could type this in the very long way, and you'll get 5. I'm just saying, like, if you just do that, you might not be able to solve every question. Does that make sense? Especially if, and I can't guarantee this, like, I'm just preparing you basically for anything, but if they give you a diploma question like this, where they give you X's, Y's, and Z's, you can't type that in your calculator, right? You guys still good? What time is it? Okay, I do have too many examples. Let me do 2 more examples and we'll take a break, okay? So I want to try doing this one right here. Let's try to solve this thing.
So you can turn it into a...
We can turn it into a logarithm. I actually want to do that second, though, because we learned how to solve this already. One of the things I showed you how to do is to go y1 equals 3 to the x minus 1. y2 equals 20. And I think it's actually on the next slide here. You guys see how you could solve it? You could type in 3 to the x minus 1, 3 to the 20. Get a graph of these things and find where they cross. That would totally work. And I hope you have that skill, because it's a good skill to have. But there is something else you could try. So let me just leave this slide right here. You could basically get a graph, find where they cross, and where they intersect. That's your answer. But what I've shown you today is you might even be able to do it by hand as well and do it like during an algebraic process. So far, so good. Let me show you another way of doing it here. What we could do is use logarithms. Can we convert this into a log format?
Yeah.
Sure. We need log with a small base down here of this number equals that number. We have to get them in the right spots, though. That's the hardest thing here. Is you've got 3 numbers, you got to put them in the right places. So what goes here?
3.
3 is correct, yeah. Because 3 is this guy's base and it's that one's base.
X minus 1 is the equals, isn't it?
That's that one.
120.
And that was 20. So let me rewrite it a little bit nicer. This is log base 3 of 20 equals x minus 1. Hang on. Log base 3, 20. Does 3 actually go into 20?
No.
But isn't this just some number? So although I have been preaching, yeah, do it by hand if you can, once you recognize, hang on, 3 doesn't go into 20, this is just a number. Right? All I have to do is find that number and add 1 to both sides, and I'll have x by itself. This is whatever log base 3 of 20 is as a number, add 1. See what I did here? I took that minus 1 from the side, I brought it to the other side. So type in log 20 divided by log 3, and then add 1.
Just 3.7.
What'd you get? 3.7?
Yeah, 3.7.
Let me go back a slide here. Here is where we found them cross. Look. They crossed to 3.7. Potato, potato. I mean, you have 2 different ways of doing this. The reason why I want to show you the second way is if you have a choice, honestly, find where they cross in the graphing calculator. It's so easy to do that, right? But they might show you somebody's work and ask you where they made their mistake kind of question. And so that's another option, is you could solve these things algebraically. Try another one. Let's solve this guy. Let's convert it into a log. We need a log with the base of a number to equal that guy. What goes where?
5 is the base.
5 is definitely the base, because it's the base of the log is the base of the exponent.
And then 104 is like, no, isn't it? Yeah, right there.
Yeah, because you're going to go 5 to the power of x plus 4 gives you the 104. So this means you need log base 5, 104 equals x plus 4. This is, yeah, essentially, what you need to recognize is that that's just a number. I don't think 5 actually goes into 104, right? Just try it real quick. Can you do log 104 divided by log 5? It's got to be,
2.8.
yeah, right? 2.8, right? Because 5 squared is 25, but 5 to the 3, I think, is 125, so it's, yeah. Right? So that's equal to x plus 4, so minus 4 from both sides.
It's negative 1.1.
1.1. Cool. You know what? There's a chance that that just might be faster than typing in your equation, typing in your other equation, resetting your window size, and finding where they cross. You know what I mean? Like, both should work. This one might be faster, though. I think this one's very reliable. Does that make sense? Like, I feel like if you're good with your graphing calculator, finding where things cross is, you're probably solid at that. How about this one? What makes this one challenging?
They both have exponents.
They both have an exponent. This is kind of a pain in the butt. Now, first thing I want to point out here, this is me being thorough again. I don't know that you'll get something quite this mean. You could. But I'm just covering my bases just in case. There's one more thing that you could do.
Can't you cancel out the x's because they're on both sides of the numbers?
Yeah, the problem is one is, like, this is a binomial. It would be like if I gave you x plus 1 over x minus 1. Are you allowed to cancel like that? Yeah. This is a binomial. So that doesn't actually work. So there is one more possibility. What you do is you treat this as though a logarithm is an expression. You know how you're allowed to, like, say, square both sides of an equation? As long as you do it to both sides, that's allowed. What you could do is you could add 1 to both sides of an equation, so long as you do it to both sides. That's allowed. One more trick you have up your sleeve is you can add a logarithm to both sides. So long as you add a logarithm to both sides, that's actually valid. Because a logarithm is just a mathematical expression. So what you now have is the log of 2 to the x minus 1 equals log of 3 to the x plus 1. Okay, on its own, that might seem crazy. Like, you might say, why would I do that? Now I have 2 logarithms. I hate logs. Logs suck, right? But there's actually a really clever trick behind this. See how this is an exponent? What are exponents allowed to do?
You can put it in front.
And so what you can now have is x minus 1. I'm going to put it in a bracket, times by the log of 2. And you can do the exact same thing right here. Take that x plus 1, throw it in front. I'll put it in a bracket again, and make it x plus 1 times the log of 3. Okay, at first glance, this may not seem like you made it better. Like, you might say, my goodness, this is getting worse, but it's actually going to look really nice in one step here. Log 2 is just some number. Type in log 2 in your calculator. What is it?
31 something.
Check.
5301.
That'll work. What's log 3?
5477.
Now it's actually not so bad. What we do is we use the logarithms. Like, we're really using them for one really cool trick. You put a log on both sides. In doing so, you're allowed to pull this guy down in front. Does that make sense? But then you say, well, okay, now we actually don't want U logarithms anymore. So we really are using them in that sense of the word. Because then you say, well, I don't want to have log 2 anymore. Let's just make it a number again. So log 2 is 0.31. Log 3 is 0.477. Now we just solve it as though it's like grade 9 algebra again. What you're going to have here is, you have to FOIL this technically. So you're going to have 0.31x minus 0.31. And then over here, you're going to have 0.477x plus 0.477. Basically, times this number by both of them, and times this number by both of them. Okay, if I were to tell you 2x plus 5 equals 3x minus 7, can you solve that? You just bring all your x's to one side and all of your other numbers to the other side, right? The only downside, this is kind of crappy, but like, you've got decimal numbers. But I mean, so maybe like subtract 0.31x from this side and 0.31x from that side. Okay, I need someone to give me a hand here. Can someone find me the exact number, like 0.477, whatever that was, and then subtract 0.31, whatever that was? We need to know what those exact numbers
It
are.
was 0.176 because Shorty read it out wrong.
Oh, this is 0.31?
301.
0.
Oh, 301.
That's funny.
So I've been going on that the whole time.
Come on, Shorty.
You corrected me right away.
Should have corrected me though. Here I am letting the rest of the class be correct.
0.176.
So 0.176?
Yeah.
Okay. Plus 0.477. And then, well, we don't want this 0.477, so subtract it to the other side. So what is that? That's a 301. Okay, I should be able to do that. That's going to be 0.778 negative.
Is negative 0.176.
What'd you get?
For I don't know.
Oh,
I got something. I got the same numbers. I got negative 0.176. Is that what you got? That's I don't know.
Okay, so it looks like what I have here is you have to take negative 0.778 and divide by 0.176. That's really
I got 301.47. I don't know. My calculator is glitching out.
Okay, here. Why don't I do this on the board just to make sure everybody gets it as well? So,
I just typed it into the graphing.
did you graph it?
Negative 4.4.
Okay, let's check and see whether what you did graphing gets us the same thing here then. So, I believe I should be taking 0.777. Sorry, I need a negative. Oh goodness.
Where did you get that point?
Because I took this number over here and brought it to the other side and subtracted it away.
Yeah, like I subtracted 0.477 to the other side, and I got a different number than you.
Okay, so you would have brought in this 0.301 that way and made that a 176.
Yeah, for X.
Okay, but then this is a negative 301, and then you got to bring this 477 the other way, so you got to subtract 477. So then I think it should be.
Oh, I got it. I got it now.
You're good now? Okay. So negative 0.778 divided by 0.176. Keely, what did you get when you found where they crossed?
I got
Negative
negative
4.4.
4.4.
Oh, same thing. Okay, the reason I show you this is not because I ever want you to do this. I would not recommend doing what I just showed you there. I would like you to see that in case they give you the question where they say find someone's mistake. Does that make sense? Because I think the fastest way of solving this is what Keely probably did, where you take these two graphs and you just find where they cross. Like that's the most efficient, right? But in case there's a question where it's like find where their mistake is, you should know that you can add a log to both sides. That's valid. The only reason why you do that is to use the log for the property of bringing the variable down in front. Then as soon as you do that, you take log 2 and log 3 and you just say those are just numbers. So just find what those numbers are as decimals. It kind of sucks because you got decimals the whole way through, but then solve it as though it's something like that. That makes sense. Okay, why don't you guys take a 5-minute break? When you come back, I think I'm just about done. I've got
2 more examples.
Yeah, I've got a couple of word problems. Or do you guys want to just do those now?
Let's just do them now.
You guys cool with that? Okay, so the last thing I want to make sure I show you is that you will get word problems. I guarantee it. Like it actually says in the curriculum, you will have to solve a word problem. I find it frustrating because it's very open-ended as to what the word problem is on. But most of the time, it basically, you're going to get an equation, you got to solve for something. Right? So here's an equation. It says there's a radioactive substance that decays and loses its mass over time. A lab had a 500-gram sample. That's where that number came from. And it said that only 3.419 grams remained after 19 days. Determine the half-life given this formula. Essentially, we have to solve for x. So let me show you some ways you could do this. The first way is we could try to take this thing and solve it algebraically. And my hope is that unless you absolutely have to, you'd recognize that this is insane. How in the world do I solve that algebraically for x? Okay, well, I actually will show you how, but I'm going to show you the fast way instead. You could start by dividing by 500 on both sides. It's not pretty, but it'll work. So 13.417 divided by 500.
0.0268.
Okay. 0.026834.
Yeah.
Equals 1/2 to the 19 over x. Then you could use the trick that I showed you a few minutes ago where, let's convert this to a logarithm. This would be log with a base of 1/2 for the number 0.026834. And that's going to equal 19 over x. Then I'm going to find what this number is right here. It's kind of gross, but I'll, okay. Log of that thing divided by the log of 0.5 means that this number right here is 5.219.
What?
I lost on that stuff. So I just found what all of this thing right here.
Yeah, but I typed in the same thing and I got a different answer. Oh, because I typed it in wrong again. What the heck? Come on.
You go.
Yep.
And then last step. How do you get x by itself? Do you guys remember from our rationals unit? Or you gotta like change those guys' spots. So like x times is up, but 5,219 comes down, so x is gonna equal 19 divided by 5,219. I got 3.6. Okay, that's doable. And I'd like to encourage you to try one or two of those. But I got a better idea. The better idea would be to go y equals, type in, let's see, 13.417. Also type in 500 bracket 1/2, or 0.5, to the power of
Miss Jack, can you please
19
call
over
100? Miss Jack, please call 100.
So I'll just type in both equations. I'm going to make my windows go a little bit bigger. Let's make this go as high as 25 maybe. I just want to get a picture of this. There's one line. There's the other one. Second, calculate, intersect. I think they only cross once, so I'll just blindly press enter. Why is it not working?
It wasn't working for me either. I had to move it.
Move the cursor over.
3.6.
Yeah, there we go. Yeah, 3.6. You have options. Oh, I mean, if it's me, unless you have to do it algebraically, which is pretty rare, they could come up. I would just find where they cross the graphic. It works, right? But especially if they're doing one of those questions where it's like, okay, look at someone's work, find the mistake, then it wouldn't hurt to know this method, right?
Mm-hmm.
That makes sense. Okay, let's try one last one, and we'll take a break here. Here's a formula. This has got like a story behind it. It's about welders, and there's a formula basically about how much light goes through a welder's facial shield. Whatever, it doesn't really matter here. What we need to do here is we need to find, if we use a shade number of 12, we have to find the fraction of visible light. So like as I read this here, it says that T is the fraction of visible light based on N. N is the shade number. So essentially what this means is that this is a 12. And we have to solve for T.
So can you like multiply by 3?
Okay, so we can try it algebraically. Let's do that first. If you do want to do that though, you have to do it in the right order. And it's actually not the 3 that goes first.
Minus 1.
It's that 1 over there, yeah. So if we want to do that, we'd have to minus 1 from both sides. So actually 11 would equal 7 negative log of T over 3.
That's going to be 33.
Okay, so then times up to 3. 33 would equal 7 times the negative log of T. Then what? Well, I don't want that 7 there, right?
Well, couldn't it be like that?
Ooh, that's clever. Let's try that. So we can take 33 and we can make it negative log of t to the 7. It's not bad. Although you're not wrong, Lisa, I actually have a better idea though. Rather than bring that exponent up,
You could divide it out.
yeah, that's usually a better idea, is divide both sides by 7. You know what though? I'm going to do one more thing. I'm going to take this negative right here and I'm going to divide out a negative 7 actually. So I'll like do that. So now what I have is minus 33 over 7 has to equal the log of t. What number is right here? It doesn't give one. Do you remember what the number is if they don't tell you?
10.
This is 10. So if I want to rearrange this now, it would be 10 goes to the power of negative 33 over 7. That equals t. It's going to be backwards because of the way I wrote it, so I'll write this on the other side. But 10 to the power of negative 33 over 7 equals t. So then, what's 10 to the negative 33 over 7?
1.93 times 10 to the negative 5.
So 1.93 e minus 5?
Yeah.
All right, that's one way.
Wait, I'm calculating.
Let's try the other one here, and then then we'll call it a break. Everybody able to follow that though? Okay, let's try the calculator way then. So, what was it? It was the number 12. And then it needed to equal, okay, this is going to be tricky here. We're going to need 7, bracket, negative log. I guess we'll have to go x rather than t, obviously, right? That's 3 brackets. Divide by 3. Come on. There's my graph. Why don't I see the other one?
I see the other one. Mine. It's just way up there.
It's at 12. I made my window size go back down to 10. So like if I change my Y max to go to 20, I think I should see it now, right? Like here's the graph up top there. Here's the graph right there. Second, calculate where they intersect. It looks like the graph starts right here. But that's not true, right? Because we talked about logarithms. This graph is going like straight down. It's got a decaying logarithm to it. So.
It's 1.93.
Yeah, 1.9 e negative 5. How much light gets through? Very little, right? That number, if you had to write it out, would be 0.000019%, I guess. So, yeah, that's why the welder's mask is so dark, right? It's trying to prevent you from burning your retinas out as you're welding. Anybody here do welding? I know Odney does, right? Okay, so let me give you a quick summary here. Logarithms. They're different, eh? And I've done 3 days with you. I don't expect you to have this nailed in 3 days. Okay. Like it's gonna take a week and a half of solid work, and even then, like you still may struggle with them. Ultimately, I need you to know, I guess, probably 3 main things. First one is I need you to know like what the shape of the graph looks like. The graph does the whole like starts straight up and then just kind of shoots over a little bit, but like it flattens out. You should know how to graph them. You should know the
Haley Servo,
rules
please
of
come to the office
logarithms.
for checkout. Haley Servo, please come to the office
And
for
so I've
checkout.
got all those rules listed back on, like, say, this slide here. And then the last thing is you should be able to solve them. 9 times out of 10, I bet you can solve a logarithm by crossing it in your graphing calculator. But you shouldn't just do that. Like, you should know how to do it algebraically as well. Okay, so here's the deal. We've got about half an hour today and an hour and a half tomorrow. Ideally, that should give you just under 2 hours of work time. Start working on that assignment. Okay. Friday, we're going to try a quiz and see how that goes. I'm going to put a few logarithms on the quiz, but like it's not just on logs. I'll throw a couple on there to see how you're handling this. Does that make sense? So there's our plan. Work time and quiz. So take a break, and then let me know how I can help you guys.